Okay. Uh, so, okay. Uh, so, what do you guys prefer? Should I pick some questions and we will discuss them thoroughly, or should I give a introduction beforehand so that you guys will be able to catch it up? Like, do you guys know what is a mineral or what a mineral is, and what are the components that are constitute to form a mineral? Anyone? It's an interactive session. Firstly, we will just introduce the key terms, that is, what is a mineral, what are crystal phases, and uh, what are the crystal systems, in what systems, how minerals crystallize, what are the silicate structures and all. Then we will move to the question. Fine? Is it fine for all of you? Yeah.
Sir, mineral is a homogeneous inorganic substance.
Uh, okay. And is it only a homogeneous inorganic substance?
Having a definite chemical composition.
Okay, okay, yes, yes, you are right. Anyone? Abhishek,
Sir,
Dheeraj?
sir,
Yes, yes, please go on. Okay, anyone? Pasavi? Anyone? No need to be afraid of. Please go on. Whatever definition you want. Yeah,
हाथ और खड़ो कर दी मैंने.
yeah, Dheeraj. Yeah, please. You have raised a hand. One by one, guys.
धीरे ले तेरे बात.
Okay, so it's fine. I
A
think.
mineral is
Yeah, yeah, please, please. Yeah, Abhishek, please.
a mineral a mineral is a homogeneous natural occurring substance having a definite chemical composition and internal atomic structure and formed by the process of nature.
Okay, okay, that's great, Abhishek. Very good. So yes, so from the interaction, I think most of you guys know what a mineral is. So okay, then I will start with the definition. So yes, you guys are all correct. In geology and mineralogy, a mineral is a species. Let's say it's a species of, broadly speaking, it is a solid substance, right? So I think anyone is presenting by mistake. Tarun, can you please stop presenting it? Yeah. So thank you, Tarun. Yeah. Okay. So broadly speaking, it is a solid substance, right? With a fairly well defined chemical composition and a specific crystal structure. So you guys were missing at one point. It has a definite crystal structure. Fine. And it is a naturally occurring substance. Now, this constituent actually form together to constitute a mineral. And one more thing there is to it, that is, the mineral are well defined, or it's bounded by crystal faces, well defined crystal faces, right? That makes a mineral. Now, I will share my screen, and I will go with the presentation. After that, we will solve questions. Okay. So, yeah. Can you guys see my screen?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So is it changing? I am changing the slides. Is it?
Yeah, yeah, we can see it, sir.
Okay.
Yes,
Okay.
sir. Yes.
Okay. Thank you. So, students, so first we will have to know that if we are dealing with a mineral or any kind of material, so we have to go through two terminology, right? One is crystalline and one is non-crystalline. Okay, there are guys in the lobby. Okay, so one is crystalline and one is non-crystalline. So what is a crystalline substance? Now, a crystalline substance is the one where the packing of the atoms are in a periodic arrangement, or it is, you can say, it is an array. So crystalline materials are metals, polymers, or even ceramics. And non-crystalline materials are the one which have no periodic packing. I mean, to say that suppose there is an arrangement, right? There is an arrangement of atoms. So the atoms are linearly arranged in a particular fashion, or they are taking a shape. For an example, let's say they are making a shape of a perfect square or a triangular shape or a pentagon. So in this case, you can say they are taking a pattern or or an arrangement. But in case of non-crystalline, there is no particular arrangement, right? So this is the term non-crystalline. It may be a complex structure or it may be a rapid cooling. So do you guys know what I mean by rapid cooling here? Anyone just can unmute yourself if you guys know something about rapid cooling or chilling. Anyone? What is rapid chilling or cooling? Anyone?
Rate of cooling is very fast, sir.
Yes, yes. So please, can you give me an example? If any rapid cooling structure, how or anything. Have you guys came across the term glass? So in geology or in earth sciences, we frequently use this term rapid cooling. So for an example, there are two type of structure textures or structures you guys I think know. That is, one is the fine grained and one is the coarse grained texture, right? Generally, when the magma is coming out from the subsurface and when it hits the surface, it can come in two ways. One is it can ascend very fast and it can ascend very slow. When it ascends very fast, the temperature difference, actually the change in temperature is very rapid. So in the subsurface, for an example, it may be of a very high temperature, let's say 900 degrees Celsius or 1050 degrees Celsius, right? But when it ascends to the surface, the temperature drops down suddenly. So as the temperature drops down at a very faster rate, the structure or the textures which formed from the sudden drop of temperature are the quenching textures or structures. So suddenly, in place of forming a well-defined crystalline rock, it actually forms glass due to quenching or rapid cooling. Okay. So these are non-crystalline in nature. So this is what I mean to say. Now we have also across the term amorphous. Amorphous is actually non-crystalline in nature. Now, crystallography in this experimental science or arrangement of atom in solids, we have came across the term crystallography, right? So generally, you have a subject in or you have a course, I think, that is crystallography and mineralogy. So this crystallography is the term crystallography has been derived from the Greek word crystallon, means cold or frozen drop, with its meaning extending to all solids with some degree of transparency, and grapho means right. So this crystallography term we used for the crystalline substances or a material which have been crystallized from some kind of melt, right? So basically, uh, if there is a mineral, let's suppose there is quartz, or there is a mineral, or let's say the mineral called olivine. So you guys all know olivine. Hello.
Sir, a green color crystal.
Yeah, exactly. A green color mineral. It's a olivine. So now, Pasvi, as you have mentioned, olivine, can you tell me what will happen if I heat the olivine mineral? Suppose I am heating the olivine with very high temperature, let's say 1500 degrees Celsius. What will happen to the mineral? Will it be in the crystallized in the solid form, or will it melt? Pasvi, can you tell me?
No idea, sir.
Uh, so, okay. So, Pasvi, if we heat any mineral or any substance, I think it will start to melt. And the certain point is, for an example, there are some mineral whose melting temperature is less, and there are mineral whose melting temperature is very very high. Right? Yeah. Anyone having any question? Okay. If you guys have any question or any doubt, you can also type. Okay, I will just see you and I will try to convey the answer to you. So, uh, if we heat it, it will melt at a certain point of time. So, for an example, there are mineral. Let's suppose there is a mineral quartz, there is a mineral biotite, there is a mineral muscovite, there is a mineral olivine. So, all these minerals have different melting point. Okay, some are having low melting point, some are having high melting point. So certainly, the mineral olivine has also have its melting point. So for an example, if we heat the mineral olivine at low temperature, for an example 500 to 600 degrees Celsius, it will not melt because it has a higher melting temperature. For let's say around 1000 degrees Celsius, let's assume that the olivine has a melting temperature of around 1000 degrees Celsius. So at 500 degrees Celsius, it will not melt, it will be in its crystalline form. Let's say a mineral A and a mineral B. We are hitting the mineral A with 500 degrees Celsius, and the mineral A has a melting temperature of 1000 degrees Celsius. Then if we are hitting the mineral A with 500 degrees Celsius, then it is very obvious that it will not melt. But on the other hand, we are melting mineral B, and let's say suppose that the mineral B has a melting temperature of 400 degrees Celsius. We are assuming, right? It's a hypothetical case, and we are treating the mineral at a temperature of around 500 degrees Celsius. Then it is obvious the mineral will melt. You can also take the example of ice at 0 degrees Celsius. Water at 0 degrees Celsius, it becomes ice. But when we increase the temperature gradually, the ice starts to melt. Okay, I'm just taking the example of water for your consideration, and we can repeat this process with any kind of mineral, right? In experimental petrology lab, if you have anyone, if ever have visited an experimental petrology lab, they work with different minerals. They treat the minerals with different temperature and pressure conditions to see the stability state, that is at what temperature and pressure the mineral is stable. Stable means it is in its crystalline state. I mean, it is not breaking down, right? So for an example, diamond is the hardest mineral of all. ठीक है? So it can sustain a very high amount of pressure. I mean, the diamond itself has formed at a very high pressure, right? But what do you think, guys, that if I place a mineral quartz, which is very very soft, not very soft, which is much softer than diamond, will it be able to sustain the pressure of diamond? What do you guys think? Can it sustain the pressure of diamond?
No, sir.
Yeah, exactly. It cannot sustain the pressure of diamond because the pressure or temperature, let's say, it can withstand, it's very very less as compared to diamond. Acha, do you guys know about the Moho scale of hardness?
Yes, sir. Yes, sir.
Okay. So Dibyaranjan, can you or anyone from this, uh, can anyone tell me what is the oxide mineral in the Moho scale of hardness? What is the oxide, silicate oxide, uh, which is present in the Moho scale of hardness? Anyone? No need to afraid. Anyone can tell.
Sir, quartz.
Yes, exactly. Quartz is the silicate oxide, uh, which we can find in the Moho scale of hardness. And can you please tell me, Dibya Ranjan, what is the Moho's hardness number for quartz, which have been assigned and followed globally?
7, sir.
Yes,
7.
yes, exactly. 7 is the number which has been assigned to quartz. So in Moho scale of hardness, there are basically 10 minerals ranging from talc to diamond. So talc being the least hard, I mean the softest mineral, and the most hardest is the diamond, which is having a Moho's hardness scale number of 10. So generally, the scientists have assigned diamond as the hardest mineral of all, right? So, yes, now I will again come back to the PPT. Okay. And yes, student, the picture you can see right now. Yes, student, can you see this picture? There is a picture.
Yes, sir.
Yes. So, students, this is a picture have been taken with the help of a microscope, right? So, this picture is known as the TAME image. So, the TAME image is the transmission electron microscopy. Okay. So, it is a very powerful microscope. Through this microscope, we can actually magnify into a very, very greater detail. It is about a very high resolution microscope. So basically, students, I think you guys have seen a microscope, and many of you have also used them also, right? In your mineralogy lab classes.
Yes, sir. Yes, sir.
Yes, yes. So as you have used microscope, so similarly, this transmission electron microscope is a very powerful microscope. Okay, these microscopes are basically used to see the image of atoms of a particular mineral structure of a particular mineral, to see the arrangement of atoms, how the atoms are basically arranged or constituted to form a mineral, right? So this is a very high resolution image. Now, so yes, now in the previously what I have said, that to constitute a mineral, we need to have well defined crystal faces, right? So what is a crystal? A crystal is nothing but a solid material in which the components are tiny atoms, right? And which are arranged in a definite pattern, which I have already mentioned. And students, they have a regularity. So okay, yeah, so they have a regularity. Now what I meant by regularity is that, so I think you have came across the term crystal faces, right? So there are faces 100, 101, 110. uh, so what are these faces? So basically, guys, do you know what are the crystallographic axis, right? Yeah, guys. Yes, I think you must be know all these basics. So there are crystallographic axes, right? We generally consider the crystallographic axis A, the crystallographic axis B, and the crystallographic axis C. So if a crystal face having the Miller indices of 100, it means it is intercepting the A axis. It means that if we in a three-dimensional space, if we assume that one axis is run towards you guys and one axis is if one is running towards you, and if one is running parallel to the screen, and if one is vertical, then let's assume the axis or the imaginary axis which is running towards you, let's say it is a parallel to the display is B, and the vertical axis is C. Now if a crystal face having an intercept like 100, it means the axis which is running towards you, it is intercepting that axis parallel to the vertical axis C and parallel to B. So this is 100 plane, right? Do you guys agree with me or not, students?
Yes.
Yeah, okay. So this is 100. Similarly, an crystal face which is intercepting the B, it is will be 010, and if it is intercepting to C and parallel to A and B, it will be 001, right? So this way we form the crystal faces, and the notation or the number I have used is the Miller indices. Okay, and we I think you guys know the Harman-Mogwin notation, guys. Hello. Yes. Munu Chinera, I think you have raised a hand.
यस सर.
Yes. Do you have any question?
नो सर. आपने
Oh,
अभी पूछा ना हरमान मार्जिन सिबल के बारे में.
okay, okay, okay. Yeah. If you guys have any doubt, you can always stop me and ask me what is what you if you guys have any kind of doubt. Okay, please feel free to ask. No need to just hesitate or something. And students, actually today is the first class, that is why I am going with all the basics, so to clarify your, and you will also get a revision from this basic class. So please, if you guys have any kind of question or any kind of question, please feel free to ask me. I am there to help you with whatever I can, right? So yeah. So we will encounter a term unit cell while studying crystallography. Now, what is a unit cell, or what basically a unit cell is? So unit cell is the smallest unit of volume that permits identical cell to be stacked together to fill a space. Right? Now, what is the meaning of this sentence? That, so for an example, you know, right? You guys have came across the term cell in biology classes in class 9 or 10, right, student? I think you have came
यस
across the
सर.
term cell. So a cell is
यस.
nothing but a building block. Okay, a cell is a building block. Now, so similarly, as cell, we the term cell have been used in biology. In case of material or earth sciences, we use the term unit cell. So it is the smallest unit of volume that permits an identical cell, or let's say, let me introduce the term unit cell to you guys, like, so if a smallest unit, say for an example, let's take it as a cube or a square. Now if the unit cell square, if we repeat it in order arrangement pattern, or in equal distance, for let's say we have taken the distance vector as a, and we are repeating that unit cell. Okay, so if I repeat it in unit distance and in a specific or constant distance a, so for an example, in a 5 into 5 grid, so what you will get, you will get a square matrix of 5 into 5, right?
यस सर.
Yeah. So, and we know, if we consider a cube, for example, a cube which has a volume of x cube. Okay, so the sides are x into x into x. Now, x has a specific distance. So, there are how many faces of a cube? Tell me. What is the number of faces a cube have?
6.
Okay, 6 faces. Now, if we are taking a very small unit cell of a dimension a, and we are uh, repeating that unit cell in a square matrix form having a dimension of x, okay, like a very small x distance, a small x, small x, small x, small x, and this 5 unit of repeating of small x will give me a big X. Okay, now if I uh, stack this array and if I repeat itself 5 times again, I will get the face of a cube or not? I should get the face of a
Yes,
cube,
sir.
right? Now see, for repeating each unit cell, let's say 5 times, from left to right and from top to bottom, we are getting a single face. Now if we stack or if we repeat this face several times, I think probably you will get the shape of a cube, right, in 3 dimension. Do you guys agree?
Yes, sir.
Yes. So this is basically the three-dimensional concept of an unit cell or a cube, let's say cube. And here in this case, we have assumed to be a cube, and you can do this experiment, or I think you can, you guys, it's better to draw it in your copy at your free time. You can guys see that not only cube, you can guys take any shape, just take the motif or the unit cell, just try to imagine like try to repeat it in a constant distance, and I think you will get the desired figure which you want. So this is a DIY experiment or do it yourself assignment. You can do it at your free time for just your better understanding, nothing else. Now, uh, yes. So I think you guys know the term crystal system, right? Yeah, guys.
Yes, sir. Yes, sir.
Yeah. So so as I've already told you that crystal is a periodic or repetitive arrangement of motifs, or that can be atoms or ions, so that we can get a perfect symmetry. Now, as I am going deeper to this subject, we will get some term or terminologies, right? Just like symmetry. Now, what is a symmetry? The symmetry is basically a periodic pattern of a repeated motif. Okay, so if we are repeating this,
So
suppose,
can you just go to the before slide once?
yeah, previous slide.
Yeah.
Okay, this one,
Yes, sir.
yeah, yes. Any question?
No, I just wanted to write notes of it. Thank you, sir.
Yeah,
Yeah, no, yeah, I can continue.
okay, 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 okay. Now, guys, the question is that if we are repeating, right? If we are repeating the pattern. So, for an example, let's say, what is this movement? This is the movement in which we are repeating each motif is known as a shifting movement. Now, this shifting movement is called translation. Now, these terminologies can be described mathematically with a term. Can you tell me what is the mathematical property that can be explained or that can be used to define this kind of term, to this symmetry terms? What is the mathematical term that we can use? For an example, for let's say you all have came across that term in your class 12, which have a directional property. Can you tell me?
So vector.
Yes, exactly. The vector. So the vector has a directional property. So guys, when you are actually repeating these motifs, na, so you guys are repeating these motifs in a particular direction, and you even see that the crystallographic axis has also particular direction. When I have said that one of the axes have been directed towards the screen, towards you, it means I am referring to a certain direction. And similarly, when you are telling that one of the axis is running parallel to that of the screen from left to right, it is also pointing towards a certain direction. So the directive property is very, very important when you are telling or you are describing a translation movement or a repetitive movement. So always remember to mention about the directive property. So I will continue again. Now, uh, the total set of such symmetry. Now, you guys have also came across the term that there are many kind of symmetry elements, right? One is the you guys know, one is the mirror plane symmetry that you all know about. uh, One is the inversion symmetry, right? So there are basically fold axis in which this symmetry can be described. Fold axis. So if let's take an example of a circle. Let us assume a circle, right? A circle has 360-degree. If you take a point and you just continue in a spherical form, and if you just draw a 360-degree line from 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, 6 degree, and if you continue this process till 360-degree, until and unless you get back to the same point from where you have all been started, you will not get a sphere, right? Or a circle. In 3D it is sphere, and 2D it's a circle. So you will get a perfect circle after a 360-degree rotation, right?
Yes, sir.
So similarly, this rotation axis of symmetry, we will also, so this is another term, the rotation axis of symmetry. So basically we use this rotation axis of symmetry. Okay, guys are still coming. Okay, it's not a problem. So we actually, why you use the term rotation axis of symmetry? So for an example, let's say there is a block. For an example, yeah, let's say I don't have anything with me right now. Yeah, so let us assume let's assume this phone, right? So it has a surface. This is the surface. Okay, now I am rotating this surface. This is 90-degree and this is 180 degree. So although this is not the same surface, but for understanding, please assume today I am not have I do not have any wooden block with me, so I cannot show you it's clearly, but please assume that this surface and this surface is same. Okay, so this is the initial position from where I have started. Now I will rotate it 90-degree, and from 90 to, again I will rotate it 90-degree. So this is 90 into 2, 180-degree, and we are getting the same surface. Okay, so it is a fold axis of rotation. I mean, so if you can guys understand that I am rotating this mobile phone by keeping an axis fixed, right? So can you tell me what is the imaginary axis I have fixed to rotate this phone?
One, sir, one.
One means I didn't get it, Dibyaranjan. Can you please elaborate it? One means,
Sir, A.
yes, exactly, A. So so the imaginary axis which is running towards you, I have fixed that axis A, and I am rotating by keeping the A constant, and so uh, keeping the A constant, and I am rotating this mobile phone. So this, by keeping of this A axis constant while I am rotating it 180-degree, I am getting the same surface. So what fold of rotation is this? I think you guys know it.
Twofold.
So
Yes,
twofold.
yes, exactly. This is a two-fold axis of rotation. Exactly. Now, for yes, exactly. Now, if this axis of rotation is, let's suppose, uh, if this similar rotation, if I get it with a 90-degree pattern, means, so for an example, let's consider this is a face, crystal face, and I am obtaining this crystal phase after every 90-degree of rotation. So let's assume this phase I am getting, this is a 90-degree, I am getting the same phase. 90-degree, I am getting the same phase. 90-degree, I am getting the same phase. Now this fold of axis of rotation would be a four-fold axis of rotation, because at four-fold or at four consecutive steps I am getting the same initial phase from where I have started, right? So this is a four-fold axis of rotation, right? So I think it's clear to all that how we get the fold axis of rotation. I think it should be clear. And similarly, if you want to get a threefold axis of rotation, or you want to get a six-fold axis of rotation, as per convenience you will get after each 60-degree, because if you do 360 divided by 6, you will get 36 and to 60. So after each 60-degree rotation, if you are get a consecutive phase and you are getting back to the same phase from which you have started, so this will define your fold axis. But students, I think you must be knowing that there is no five-fold axis of symmetry. Can anyone tell me please why we do not get five-fold axis of symmetry? Anyone?
Sir, it's not divisible by 360 degree.
Yes, yes, yes.
It cannot be divided by 360 degree.
Uh, no. Actually, it's not like that. It cannot be divided by 360-degree. So let me ask you one thing. As you have tell me that telling me that you cannot divide it by 360. So cannot that is it not that 360 can be divided by 5, right?
It can be divided by what?
It can be divided by 5, right, students? I think you can divide it by 5. 360 can be divided by 5, right?
Yes, sir. It
Yes,
can be
sir.
divided.
And what will be the degree if you divide 360 by 5? What will be the answer, students? Hello, anyone?
72,
Yes,
72.
it is 72-degree. So so yes, Rajesh, so you are telling me that it is not divisible by 5. Yeah. I think you know the concept, but I think there is some we have to garnish the concept what you have, right? Rajesh, can you unmute yourself?
Yes, sir.
Yes, yes. So please, yeah, let's interact. So so as you guys have only told me that 360 by 5 is 72-degree, right? So if 360 by 5 is 72-degree, it means it is divisible by 5. But the fact is, if you do a cos or sine of that number, so if you guys can do that, cos of 0-degree is 1, cos of 90-degree is 0. But if you guys do a cos of 72-degree, do you will get 0 or 1 or any a whole number? I think you will not get a whole number. You will get a if in fractional terms. Now the question is, if you are getting a fractional term in the symmetry operations, it means or it states only one thing, that as if you guys want to repeat the pentagonal motif in a three-dimensional space, listen it very carefully. If you repeat the pentagonal motif, or so pentagon has 5 sides. So if you guys let me clear one thing, that so if you have a square, right, or if you take a square in 2D, you will get only 4 sides, and in 3D you will get all the 6 faces. So if you guys take any of the face and just try to connect the base of any square to that face, it will just arrange it a stacked motion from each of the connecting points. You will get a definite arrangement in all the 3 directions, or in the nth dimension as possible. But if you take a pentagonal motif, just try to draw it in your copy and see that if you want to continue the stack from each of the sides, you will not be able to do that. there will be a certain point of time when there will be a particular gap in that three-dimensional space or in the 2D for case of a copy. That is the reason why for we five-fold symmetry does not exist. Okay, five-fold symmetry does not exist. But yes, in chemistry or in other material sciences, it is possible, but it is possible with help of certain kind of environments. We'll come that point later. How we can do that? That's a very complex part. We will do that later. Okay. So yes. So there are certain symmetries. One is rotational symmetry, one is translational symmetry, and there are some point symmetry also. Now, as I have talked about the point symmetry, so there is a concept of center of symmetry. So do you guys know what is the center of symmetry is? Or I'm just explaining. So if anyone know, can explain it to the class also. So a center of symmetry is nothing but, so when you are considering, for an example, let's suppose you are considering a sphere, and so the sphere has a radius of let's say it has a radius of, for an example, 10 centimeter. Okay, or you are drawing a circle or sphere, constituting a sphere which is having a radius from its very center. Just imagine it as a three dimension. In a three-dimensional, we are here in this three-dimensional space. So, and it is having a point, central point, and I am considering the radius of the sphere to be 10 centimeter. Now, guys, uh, so if it is a sphere of radius 10 centimeter, now if there is a point, okay, so there is a point, let us break this sphere into quadrants. For an example, four quadrants, let's suppose draw four quadrants, and each of the quadrant is having an upper hemisphere and a lower hemisphere as well. So first, second, third and fourth. Okay, so we are having a point, or we are having a point in the first quadrant, and if you extend the point from the first quadrant to the central portion towards the uh, third quadrant in the lower hemisphere. Can you imagine this? You are taking a point, and you are taking basically 2 points, one at the first quadrant of upper hemisphere, and another one at the third quadrant lower hemisphere at the lower part. If you extend or draw a line from this first point to the point at the third quadrant, then it will exactly pass through the center of the sphere, and it will go towards the third quadrant at the lower hemisphere. So you have taken a point at the upper hemisphere, and that point is corresponding exactly in a 180-degree opposite to the point, but in reflecting in the lower hemisphere. Then that line will pass through the center of the sphere, and it will tell you that the, in this case we have considered a sphere, it can be any kind of a mineral block, let's suppose, let's say. Now if this happens, then and only that figure or that block will have a center of symmetry. Okay, do you get it, guys? Have you got this point, what I have
Yes,
been
sir.
trying to explain?
Yes, sir.
Yeah, okay. So yes, see, can you guys see the picture of the center of symmetry?
Yes, sir.
Yeah, so
Yes, sir.
yes, so this is exactly the center of symmetry, how it works. So see that what we are doing. So this point, let us take this point. This is my mouse cursor. I am taking this point. So see students, this point have been traced. So it has been traced with a line. It has been passed through the central point, and the point has been projected backward. But see one difference. This point is in the upper hemisphere, left hand side, and in the right hand side, the same point has been inverted and in the lower hemisphere. So this point which consists of a particular marking on the left hand side, and we are getting the same marking on the right hand side, but as it seems like an inversion has been occur in the opposite side but in the lower hand hemisphere, so that the line which is constituting these 2 points, this is the point A and this is the point B on the right hand side. Let's assume it has, so that it seems like it has been passed through the center of these two faces, will exactly give you the center of symmetry. So reflection, it is also a basically reflection, but it is a reflection of a point through inversion. It will create a center of symmetry. Remember, always remember this. When a reflection is there of a point through inversion, it produces a center of symmetry. Okay. And this is the mirror symmetry. See, for an example, you have written H, you have passed a mirror and you are getting the same H. So this is a mirror symmetry. If you will do I, you will get the same I. If you will draw an O, you will pass a mirror to that O, you will get the same O without any changes. This is the reflection symmetry in two direction. You are getting a mirror symmetry in two direction. Okay. So students, you have you already know that in vertebrates we also get a symmetry, right? We all are vertebrates. Do you guys agree or not? Right? We are all vertebrates, right?
Yes, sir.
We have a vertebral column running through our back, this spinal cord. It's running through our back and to this point. So as we humans have vertebral columns, we also have a symmetry. Means if anyone just draw a line from the middle part or the central part of a human being, a line or an imaginary plane will run through it. But the symmetry what we have is known as the bilateral symmetry, right? So I think I can give give me a just, it's a mind assessment task, just just to it's for fun. uh, can you guys tell me, it's a feature seen in one of the invertebrates which shows a pentagonal symmetry. Can you tell me what is that thing, or what is the name of that invertebrate which shows a pentameral or pentagonal symmetry? It, or sometimes it's,
Starfish.
yes, yes,
Starfish.
except starfish. If you guys don't know, it's okay. You guys can find out what will be the answer, and I will ask you in the next class. It's just a it's a mind game type of thing. You guys can find it. It's very interesting. It's an invertebrate. Okay, and we used to get that invertebrate uh, many years ago, and at some point of geological time it shows a pentameral symmetry, a five-fold symmetry, or sometimes it also known as the radial symmetry. Just try to find out. It's very interesting thing. The specimen is,
Sir, Echinode.
yeah, exactly, echinodermus. Yeah, very good. Yeah, so so as I was talking about previously about the symmetry axis, a triangle, it's a threefold symmetry axis representation. A square is a representation of the fourfold symmetry, and a hexagon is a representation of the sixfold symmetry. Now, there is also a term called the roto-inversion. Now, what is a roto-inversion? Basically, is roto-inversion is nothing but a roto-inversion is a type of symmetry operation which involves both rotation, means you are rotating an object, and you are inverting that object. So by combining a rotation operation with an inversion operation, you will get a roto-inversion symmetry. Yeah. Yes. Now let's move to the crystal system, right? So as you know, there are 32 crystal symmetry classes which are in existent in this universe, and the lowest symmetry is shown by the triclinic system, and the highest symmetry is shown by the cubic or isometric system. So there are mainly 7 crystal systems. I have written it here 6 because one I have just write the original division, that is the hexagonal system. It has basically one subdivision which is known as the trigonal crystal system. And so tell me, for let's say there are 6 or 7 crystal systems. Okay, we will be dealing with 7 crystal systems. Now, as we are dealing with 7 crystal system, each crystal system has a normal class. Do you guys know what a normal class is?
सर वो जो होता है ना हाईएस्ट डिग्री ऑफ सिमेट्री एलिमेंट जो क्लास शो करता है वही उसका नॉर्मल क्लास होता है
Yeah,
सही
exactly. So you guys know it. So a normal class is the one which having the highest number of symmetry elements. So 4 by m, 3 by 2 by m, it is also a normal class. So 4 by m, 3 by 2 by m is a normal class of which system? Of which crystal system?
सर
Cubic, sir.
क्यूबिक
Yes, yes.
क्यूबिक
Cubic.
Yeah, exactly. Very good. Very good. It's a cubic. It's crystallized in the cubic system. And do you guys know the name of that particular uh, that class 4 by m, 3 by 2 by m?
सर सर शायद से हेक्साऑक्टाहेड्रल
Yes, very good. It's hexoctahedral. Now, why is it hexoctahedral? Uh, who is answering?
सर शायद से वो जो उसका 48 फेस होता है ना इसीलिए
Okay, okay, okay. Very good, very good. So you guys know this thing already. Yes. So hexoctahedral. Now, similarly, the tetragonal and the hexagonal system have also this kind of normal classes. In case of hexagonal system, the normal class is 6 by m, 2 by m, 2 by m. So I must be guessing that you guys know the name of this system. 6 by m, 2
तो
by m.
शायद से डाइहेक्सागोनल डाइपिरामिडल क्लास
Yes, very good. Dihexagonal dipyramidal class. So it's a dihexagonal dipyramidal class. So for those who are new to this geology, who are first year students, so what is a dihexagonal dipyramidal class? It is nothing. It consists of two pyramids, one at the top and one at the base, and it's dihexagon in nature. Dihexagonal. So it is a pyramid of two hexagons. So one is having at the top and one is the bottom, and this dihexagonal dipyramidal class you can just having a horizontal mirror plane. Horizontal mirror plane in dihexagonal dipyramidal class 6 by m, 2 by m, 2 by m. In tetragonal system also you have a Harman-Markov notation of a class, that is 4 by m, 2 by m, 2 by m. So do you guys can anyone please tell me, please, those who are answering apart from them, those who have not answered till now, can anyone tell me what is the name of the 4 by m, 2 by m, 2 by m? Yeah, anyone, guys?
यस सर
Yeah,
सर डाइटेट्रागोनल
yes,
डाइपिरामिड
yes, very good. Ditetragonal dipyramidal class. So you guys already know this. So yeah, so see this. So this is the general configuration, cubic or isometric system. So as I have telling you previously that there is a concept of the crystallographic axis. So there are basically 3 crystallographic axes, A, B and C, and as you can see, the 3 crystallographic axes in case of a cubic or isometric system are all equal in length and intersect each other at right angle. So the A axis, the B axis and the C axis, they intersect each other at 90 degree, and the 3 crystallographic axes which are present in the cubic or isometric system are all equal in length. So this is the general configuration of isometric system, right? So similarly, so as I was telling, the at a glance, the hexoctahedral class or the hexatetrahedral is the normal class of the isometric system, which consist of 48 crystal faces having the highest degree of symmetry among all the crystal systems. Please remember this type of normal classes for each of the system, because the normal classes are always frequently asked by in the jam or in the gate examination, and this general configuration also. So out of curiosity I am asking this. So you guys are where are you guys? So you guys are BSc or master student?
BSc.
Okay, okay. So you guys are gonna give jam, right? The joint admission test for MSc. I think you all guys will be opting it for the jam. So for your exam purpose, this configuration for the normal class, the Harman-Markov notation of the normal class, these are very very important for your examination. Now we will go through the hexagonal system. So the hexagonal system has four axes. Okay, what are the four axes? The four axes are A1, A2, A3 and C. Now students, this A1, A2 and A3, these three axes are equal in length, but these are not equal to the vertical axis, that is the C axis. That is the C axis. The C axis represents the vertical axis. A1, A2, A3 meets in these three horizontal axes are equal in length, but these three horizontal axes are unequal to the vertical axis, that is the C axis. And always remember one thing, that this C axis. So for an example, if there is a Harman-Markov notation 632 or whatever, maybe 4 by m, 3 by 2 by m, can you guys tell me which fold axis will be the vertical axis in case of 4 by m, 3 by 2 by m or 622? Means the vertical axis of which fold? Students?
Yes, sir.
Which fold? For example, yes.
Sir, can you repeat? Sir, can you please repeat the question?
Yes, sure. My question is, if there is a Harman-Markov notation of any crystal class, let's say, for an example, I am taking 4 by m, 3 by 2 by m. So it's the Harman-Markov notation of cubic crystal system, the hexoctahedral class, right? So there are 4 by m, 3 by 2 by m. So there is a fourfold, there is a threefold, inverted threefold, there is a twofold. So if a question has been asked to you in any examination, that what will be the fold axis for the vertical axis in case of 4 by m, 3 by 2 by m, means the vertical axis will be of what fold? Fourfold, threefold or twofold?
Sir, if I am
Fourfold,
not
sir.
wrong, sir, I said twofold.
Yes, yes, yes.
So twofold, okay.
No, someone said fourfold.
Fourfold, sir.
Yes, 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 Divya Ranjan. Why? Why it will be a fourfold?
Sir, four type of similar face occur. So
Yes, but there is one another connotation that you can use to remember. That is, if there are any Harman-Markov notation and the highest fold axis which is present in the system will always be the vertical axis. Please do remember this thing. Okay. In case of 6 to 2, the vertical axis will be of 6 fold, because 6 is the highest number of fold axis present in that system. So 6 will be the vertical axis. So the highest number of fold or symmetry which is present in that particular system will be the vertical or the C axis. Okay. This is an important point to remember. Okay. Okay, someone is joining now. Okay, yes. Now, and yes, the A1, A2, A3, these three crystallographic axes are at 120 degree apart from each other. But there is a relation of all the A axis, that is A1, A2, A3 with the C axis. That relation is of 90 degree. This A1, A2, A3, this total three angle, this total, they make a 90 degree with that of the C axis. Okay. That was for hexagonal system. Now for orthorhombic system, that A, B, C, all the three crystallographic axes are at an equal length, means they are not equal to each other. A not equals to B, not equals to C, but the crystallographic axis A, B, C makes 90 degree with each one of them. So this is the general configuration for orthorhombic system. And you guys, I think, know a pinacoid. I think you guys know a pinacoid. What is a pinacoid?
So two
Sir,
parallel
with some
faces.
symbols.
Yes, exactly. Two parallel face. And if that two faces are not parallel, what it will form? It will form a dome, right?
Yes, sir. Yes, sir.
Yes, exactly. And for monoclinic system, the monoclinic system is, please remember all the general configuration for each one of the system. For monoclinic system, all the three crystallographic axes are not equal to each other, and the angle between alpha and gamma are 90 degree but not equal to beta. Okay, so beta is the angle between, see here what have been represented, beta is represented as the angle between A and C. Okay, the angle between A and C will not be 90 degree. Why it will not be 90 degree? As the name suggests, monoclinic. Mono means one and clinic means inclined. So from the name monoclinic, we can able to infer that one of the crystallographic axis is inclined. Okay, that's why the name monoclinic has been given. And this figure, what you are seeing right in front of your display, is an example or the figure of a monoclinic prism, right? And similarly, triclinic system, it is the system which is having the least symmetry elements. Neither the crystallographic axis are equal, they all are unequal, and the angle are also not equal to 90 degree, because each and every angle is at some angle to each other. They doesn't make a 90 degree with each other, never. This kind of system is a triclinic system. It's an example of a triclinic pinacoid. So we are done with the crystal system. Now uh, this is a Bravais lattice. Okay, so there are basically lattices, 14 Bravais
Sir,
lattices. Yes.
sir, sir. Why the trigonal system is considered as a subsystem of hexagonal system?
Why the trigonal system? Okay. So this trigonal system is why basically it is considered as a hexagonal system. It's very simple that students, if you know that the trigonal system is having a crystallographic axis angle of 120 degree, yeah, sorry, 60 degree, right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes. So it is having a angle, each angle of 60 degree. They are making a an angle of 60 degree. Each crystal faces making an angle of 60 degree. But you guys have noticed that when in case of hexagonal system, when you draw the A1, A2 and A3 system, uh, what is the angle we take for A1, A2 and A3? Anyone have noticed till now? What is the angle which is taken by A1, A2 and A3?
So, sir, say 120.
Yes, exactly. It takes an 120 degree. So the crystallographic axis, that A1, A2 and A3, because we know that hexagonal system has four axes. One is A1, one is A2, one is A3 and one is C. The crystallographic axes are at an angle of 120 degree. Now if you guys, you can do the sum. If you guys do 360 by 120, what will it will be? What can you tell me? What it will be If you guys
Three.
yes, exactly, it's a 3, the number 3. So within the hexagonal system you are getting a trigonal you are getting a symmetry of trigonal system. Are you getting my point?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes. So at a very concise and clear way, what I mean to say is, if you guys are drawing a hexagon, right? If you are guys drawing a hexagon, the hexagon will have 6 sides. Do you guys agree or not with me? I think you will all agree that hexagon having a sides, it will have 6 sides. If we just draw the cross section of an hexagon, okay?
Yes, sir.
And each of the faces or each of the sides will have an angle of 60 degree with each other. Now if you guys want to inscribe the triangle within that particular hexagon, you guys can inscribe the triangle. Okay.
Yes, sir.
Yes, so you guys can inscribe the triangle within that hexagon. So a triangle is a cross sectional which represents a trigon of a triangle. So, and it is a representation of trigonal system. So please listen it carefully. Within the hexagonal system itself, you can inscribe the trigonal system. That is why the trigonal is a subdivision of hexagonal system, because in case of trigonal system, we divided the 360 degree, the radial component of the of a circle, we divide it with 3, and by dividing it with 3 we get 120 degree, so that the crystal faces are 120 degree apart. So it is basically the same system, and as within the hexagon you can already inscribe uh, that phase change of 120 degree. That is the reason we considered the trigonal system as the subdivision of an hexagonal system. Although it is a subdivision, but as a whole, if we look it technically or mathematically, it is the same system. But for our, in case of geology or in case of material science, as the phases, there are some phases which have a relation of 120 degree, and there are some phases which having a relation of 60 degree with each other. For this simplicity, we use the subdivision trigonal system. I think it is clear to all of you.
Yes, sir.
Okay, thank you. And so there are 14 Bravais lattice. Okay, now this concept of Bravais lattice was first described by French scientist Auguste Bravais, okay, in 1850. Now he has named 14 types, different types of Bravais lattice. Now, to explain these 14 types of Bravais lattice, it has been explained with unit cell compatibility. In when these unit cell are actually arranged in a particular order, they have found that we can actually order this unit cell in 4 different kind of arrangement. I mean, or combination of 4, which will make 14 Bravais lattice for all the 6 crystal systems. So that are simple, okay, face centered, body centered, and in centered. So do you guys know that PFIC configuration? What is a primitive? What is a face centered? What is simple cubic, and what is end centered? Yeah, guys.
Yes, sir.
Yeah, so I will just recapitulate once again. So the P represents the primitive or the simple unit cell, which exactly looks like a cube. The face centered is the unit cell. It is also a cube, but in case of face centered, the difference is only is that in each of the cubic faces there is one atom each, and which consists 6 faces, and 6 atoms will be there. And in case of body centered, it is a combination of a simple cubic with a extra uh, nucleus at the center of that atom. So these are the fundamental concept which you all know. And similarly, the Bravious lattice can also be done for the primitive tetragonal, the body centered tetragonal, and the and while there is no f centered, because all the face centered will always reduce to a network of a body centered. Okay, for the tetragonal cells, because what we do in case of tetragonal is that, or what we do in case of isometric is that, if we are taking a face centered at each of the faces, the face for the upper part it will share half of the atom, and for lower part, for the lower part of the face it will share half of the atom, so that half and half makes an one. Okay, but this process we cannot do in case of tetragonal. That is why the combination of all the tetragonal face centered will be reduced to a single body centered atom, or that is why we do not consider a face centered in case of tetragonal. Okay, but in case of orthorhombic, we have all the four: primitive, body centered, end centered, and face centered. This is the end centered, because what is end centered means only the basal part will only have two atoms. That is, from this basal part, if we connect a regular orthorhomb, that the atom in that basal part will share its orthorhomb with the upper orthorhomb, I mean the upper unit cell and the lower unit cell, and no more unit cell we can connect. Or if we connect also, it will not share any atom. Sidewise, it doesn't share any atom. Okay, that is why we get another arrangement, that is the end-centered arrangement for orthorhombic cell. And this, always remember that this end-centered arrangement is only excluded to this orthorhombic and monoclinic also. And one and a very important question that usually asked by JAM or GATE, that is, please name the crystal. You guys can note this question. Please name the crystal system which contain all the four types of centered unit cells. That is primitive, body centered, face centered, and end centered. The answer would be orthorhombic crystal system or the orthorhombic cell, because in orthorhombic you can see P, I, C, and F, or you can just remember it like PFIC or PICF or PCIF, anything. These four type of arrangement are only seen in orthorhombic system, all the four, and and none in other crystal system. You cannot see all the four. This is only exclusive to orthorhombic. All the four are seen in this system. Is it fine, guys?
Yes, sir.
Okay, please remember this question. This is very important for your JAM or GATE, because in JAM or GATE they usually ask that PFIC, all the four is only seen in orthorhombic. You will guys get a, you can anytime you can get a question sooner or later like that. Please name the crystal system, or what will be the crystal system which contain P, F, and IC arrangements. So they will give you options like orthorhombic, tetragonal, hexagonal, or isometric. The correct option will be the orthorhombic system. Always, please remember. Yeah. So, uh, so the basic I think is more or less clear to each one of you. Now, guys, what I will do, I will share a PDF in this presentation mode, and we will just do a rapid question answer session. So, are you guys up to it? So do you guys want to do a rapid question answer session? I will just share a PDF. It's very easy. The questions I have collected. It's a part of the TA assignment. So are you guys ready?
Yes, sir.
Okay, okay. So I am sharing the PDF question. There are a set of many questions, and if you guys want, I can share that material with you. That set of question. Just I am sharing. Wait a minute, guys. Yeah, I am sharing the question. We will just wrap this session with the question answer. Please wait 30 seconds or so. Let me share it with you. Screen. Okay. So you guys can see my screen, right? Oh, let me check it once again that the recording is on or not. Yes, it's been recording since. Okay. Okay. So guys, please respond. Can you see the set of questions?
Yes, sir.
Okay, okay, okay. Now, let's solve. Oh, okay. And I have forgot to ask you that one thing. One second. What is? Wait a second. Wait a second. Yes. Okay. 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 Yeah. So, guys, actually, I think the NPTEL class for okay, let me minimize it. Yeah. So, guys, in the NPTEL class, I think you guys have been posted some with some assignment, right, guys?
Yes, sir.
Yeah. So, did you guys have already done the assignment?
Yes, sir.
Yes,
Yes, sir.
sir. वीक 1 का असाइनमेंट आया था उसको हमने सबमिट कर
ओके सो आप लोगों को कोई मतलब परेशानी तो नहीं हुआ उस असाइनमेंट या फिर मैं उस असाइनमेंट को और एक बार एक्सप्लेन कर दूं टू यू गाइस
नहीं सर कोई परेशानी नहीं हुई
but yeah okay after solving these questions we will just go to the assignment and I think there are only 9 questions to that assignment we will just discuss it once again okay is it fine with all of you
यस सर
okay okay
Okay.
okay 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 then so yes and please this is a set of question which has been prepared for you ये आप लोगों के लिए है ठीक है so मैं कोई anyone any random person please try to answer now I will tell you the process how to solve it okay anyone can please on your mic and please anyone voluntarily जो कोई भी आंसर देना चाहे anyone don't worry we will not cover every question we will only cover the question which we have been studying for the first week okay so yes for the first question so anyone please who knows the
सर
answer
Proton, sir.
सर
Proton.
जीरो
yes yes
the
yes
number so the number of electrons in
Proton,
natural
sir.
atom
yes the first correct the correct answer is proton yes the for a neutral atom the number of electron is always balanced by a proton yes now the second question where do the valence electron occur I think everybody
Outermost cell, sir.
uttermost shell
yes yes very good all isotopes of a given element would have the same number of yes please
सर प्रोटॉन
yes but a different number of
सर इलेक्ट्रॉन एंड न्यूट्रॉन
no not electron it should
सॉरी
be
सर
yes please go on
सॉरी सर शायद से
Neutron and proton, sir.
न्यूट्रॉन
no
न्यूट्रॉन एंड
only
न्यूट्रॉन
only to be specifically see it would be only neutron okay because to be specific it should be neutron okay for all isotope of given element the same number of there should be same number of proton but in some cases there could be the same number of electron also but the neutron number will not be same for isotopes okay please remember this and the atomic weight is also different and that is the reason we get a different atomic weight okay
यस सर
okay so what will be the common oxidant state of oxygen can you guys
सर -2
yes
-2
yes and common oxidant state of hydrogen is +1 you
सर
also
+1 and -1
yes
सर +1 and -1
why -1
सर +1 सर +1 for hydrogen and -1 for hydride
yes and the common
+2
yes very good
+1 +2
yes and so I
सर सिलिकॉन का शायद से +4
yes 4 plus common oxidant
एल्युमिनियम
aluminum
+3
yes
+3
yes
पोटेशियम K+,
okay
क्लोरीन -, आयरन +2 and +3, कैल्शियम +2
very good ferrous and ferric very good calcium is short
जी
sir
सर
of calcium
+2
Ca
+2
okay
+2
okay yes And let me tell you that do you guys know? I have one more question, that is how to solve this question. That is, the- if the question is like the oxidation state of aluminum. So the common oxidation state of aluminum is +3, but there is one more oxidation state of aluminum. Can you tell me what is that oxidation state?
सॉरी सर सर वो तो एल्यूमिनियम का +3 होता है.
हाँ, +3 होता है, बट कुछ कुछ मिनरल में तो आप कौन हो, प्लीज आपका नाम, प्लीज टेल मी योर नेम.
सर मुन्नू चिन्ह.
Okay, okay. So Munu, can you please tell me, at sometimes it's very rare also, and it is true for silicon also. Okay. Uh, at what coordination site that's both silicon and aluminum can go sometimes? At what
सर
is the
शायद से
yes, yes,
टे-
please.
सर उतना कंफर्म नहीं है सर. शायद से टेट्राहेड्रल या फिर ऑक्टाहेड्रल. सर
नहीं नहीं,
सर ऑक्टाहेड्रल सर.
yes, exactly, octahedral site. Very good, very good. It's octahedral, because suppose देखो क्या होता है, let me explain this concept to you. Why it is octahedron? Very good, Moon, very good. So why it is octahedron? Because generally क्या होता है, it only occupies a 3 plus state, okay, or for silicon it is a 4 plus state, okay, but it sometimes also goes to an octahedral coordination. Why is that so? क्या होता है कि when the 3 plus or the 4 plus sites are filled up but there are more Al3 plus, so अगर क्या हुआ, if in a classroom it has a strength of 50 student, all but 60 students have joined the class, so 50 student will only occupy the space because there are seats for limited seats for 50 student, and there are rest 10 students, they will not be able to occupy the seats. Am I right or wrong?
यस सर.
Yes, but क्या होता है मिनरल के केस में, इफ देयर आर सम एक्स्ट्रा your elements in higher energy state, they try to actually randomize. मतलब क्या होता है, the randomness, that is the del s of that state increases due to higher energy or higher heat supply. Now when the randomness increases, the extra elements can sometimes occupy that sites, or what is another case is possible, instead of going into the threefold or the fourfold side, the element of that particular coordination number or that state can occupy some higher state, for example octahedral state, okay, due to higher randomness. That's why Al3 plus and Si4 plus can sometimes goes in a state of higher oxidations, of higher आपका coordination site, that is octahedral coordination site. Is that clear?
यस सर. सर लेकिन अगर हम देखें तो फिर सर Al3+ हो गया, सिलिकॉन -4 हो गया सर. लेकिन अगर हम उन दोनों के बॉन्डिंग के बारे में बात करें सर, जो एन टाइप सिलिकॉन सॉरी एन टाइप सेमीकंडक्टर पे जो होता है ना, एक होल क्रिएट होता है सर. ऐसा भी कुछ इस केस में क्रिएट होगा या फिर वो बैलेंस हो जाएगा?
No, no, no. What it will do is, जैसे कि आप इन टाइप सेमीकंडक्टर में बात कर रहे थे, जो होल क्रिएट हो जाता है, इफ ए होल हैज बीन क्रिएटेड, जो आपका इन टाइप जो सेमीकंडक्टर होता है, जैसे कि आपका वो एक साइड से और एक साइड में जंप कर गया, तो इन इन दैट केस क्या होता है, देयर आर नॉट सफिशिएंट एटम्स, राइट, मतलब देयर आर नॉट सफिशिएंट एटम्स. तो as there are not sufficient atoms, they migrate and leaving a vacant space. But in case of excess atoms, what it does is it try to push the boundary. Okay, जैसे कि आपका, so for an example, if a region within that specific localized atom, एक specific region है जहां पर आपका only three fold coordination जो cations है घुस रहा है, they are entering a space, only threefold coordination cations are there, but but if there are excess aluminum, they will not enter that space, or if also they enter that space, suppose आपके पास 20 excess atoms है, तो उनमें से सिर्फ जो 10 10 ही एक्सेस एटम्स घुस पाए, ठीक है, बट देयर आर आल्सो रिमेनिंग 10, सो व्हाट द रिमेनिंग 10 विल डू?
सर वो शायद से वो होल को फिल अप करने के लिए अपना इलेक्ट्रॉन शेयर।
Yes, yeah. Please unmute yourself, Monu.
यस सर।
Yes. So it will try to fill up that space.
यस सर।
Yes, but it can also do one thing. As I have told you, there is an increase of randomness. ठीक है? आपको randomness का concept पता है? That del S entropy.
यस सर एंट्रोपी
Entropy.
तो
So
थर्मोडायनामिक्स का चल रहा होता है।
yes. So Monu, why entropy increases due to higher energy?
सर मुझे जो लगता है कि वो शायद आपने जो बोला ना ज्यादा अगर एलिमेंट हो जाएंगे तो फिर उसका एनर्जी लेवल थोड़ा हाई हो जाएगा सर, इसीलिए शायद से उनके सर वो आपस में शायद से बॉन्डिंग करके ऑक्टाहेड्रल स्टेट ऑक्यूपाई करेंगे सर।
Exactly. The energy जब आपका increase हो रहा है, when the energy is increasing, okay Monu, when the energy is
Yes, sir.
increasing, so what it will do? So there will be a collision between the excess atoms in the higher energy state also. Okay, so this
Yes,
is
sir.
just
Yes.
what it means. It means that the vibrational energy will increase. Am I right or
Yes,
not?
sir.
And
Yes, sir. Yes, sir.
as the vibrational energy will increase, that vibrational energy will tend to cause that particular atom to move into the higher coordination state, okay, in the octahedral
Yes.
state.
Yes, sir. Yes.
सो ये लेकिन अगर आप इस वाइब्रेशनल एनर्जी और एंट्रोपी को डिक्रीज कर दोगे तो फिर ये स्टेट नॉर्मलाइज्ड हो जाएगा, तो फिर जो आप बोल रहे हो जो स्टैंडर्ड सिनेरियो होता है वो हो जाएगा, ओके।
Yes, sir. Yes, sir. Thank you, sir.
Only possible in case of higher energy state. So
Yes, sir.
so if we go
Thank you, sir.
yes, so if we go deeper into the earth, we will encounter this type of setting. So we will see that Si 4 plus, as it only goes to the tetrahedral side. As we go to the deeper earth, so at the deeper earth आपका temperature भी ज़्यादा है, we have higher temperature and higher pressure, so the energy will also increase, right? So in case of this particular scenario, we will able to see that Si 4 plus will not only occupy the tetrahedral but will also can occupy the octahedral as well. There are certain minerals also, जैसे कि for an example garnet have a general formula of X3Y2 Si3O12, correct?
Yes, sir.
So, but this is a normal garnet. But there is another garnet called the meteorite garnet. This garnet का जो SI है, ये SI 3 से ज़्यादा है. The SI number is greater than 3. So there is an extra SI. So the extra SI does not go to the fourfold or the tetrahedral coordination side. It goes to the octahedral coordination side. Okay, this is known as the meteorite garnet. So do you guys heard about this term meteorite garnet? Anyone? I think you haven't heard this or encountered this term before, the meteorite garnet, right?
No, sir.
So please, you can note down in your copy, there is a type of garnet known as the meteorite garnet. The difference is that it has a silicon number of greater than 3. It has a higher silicon number than the usual garnet. This type of garnet is called the meteorite garnet. Okay. It might come in your exam. It is very important for exam purpose. Okay. So अगर इस तरह के questions आए तो I think you will able to solve, right? You will be able to do it, the objective questions. So I will, yeah, this is the first class, so I have more questions like this which can help you in every kind of exam or assignment. I will come up with the every possible questions which I have. So now, so can you tell me what is the mineral formula for plagioclase? कौन सा होगा?
So KLSI3.
Are you sure?
Sorry, sir. Sorry, sir. Plagioclase बोले. Sorry, sir.
Yes.
Sir, शायद से A, CANAALSI.
Exactly. CaNaAlSi2O8. Very good. And for calcite, it is very easy. CS. What will be the answer? CaCO3.
CaCO3.
Yes, yes, yes. And for K feldspar, what will be the answer, guys?
KLSI3. KLSI3.
Very good, very good. And for halite, what will be the answer? NaCl.
NaCl.
Yes. Now, who can do the for 30? How many oxygen ions are involved in the formation of the silicon oxygen tetrahedron?
4.
Yes, very
4,
good.
sir. SI 4.
4. Yeah. Now I will ask some random question. 35. Please answer the 35 question.
Sir, less than 2. 2.5, sir. 2.5.
Yes, it will be less than 2.5. Yes, because gypsum can be scratched with your fingernail. So
Yes.
your fingernail has a hardness of 2.5, so it is less than 2.5. Okay. So the hardest mineral is,
Diamond.
yes, and the softest is talc, right?
Talc.
Okay. Now move to this question. So guys, what will be the 47 question answer? What kind of bond will
Valence
form?
size.
Yes.
Covalent.
No.
Sorry.
Dipole bond.
Uh,
Di.
yes, dipole. Yes, you are actually going towards the answer. Please.
Hydrogen bond.
Uh, it's a hydrogen bond, but I think, yes, who is telling me hydrogen bond? Please tell your name.
Jivita.
Okay, Jivita, you are correct. It is a hydrogen. One of hydrogen interlinked is with it. But can you specify what kind of bond? It is a very weak bond. Anyone? Munu, Jivita, anyone?
Sir, Bhandre. Sir,
Yes,
Bhandre.
exactly. It's a van der Waals type of bond. It's a very weak bond known as the van der Waals forces or van der Waals type of bond. Very good. Very good. Okay. Now 52. Anyone will try? So this is a tetrahedron configuration, as you can see, guys. So A is the bond, smallest bond which is there, and B. So it is a normal tetrahedron configuration arrangement. So what will be this A, the blue color thing?
Sir, silicon size.
Exactly.
SI.
Yes, and B will be
Sir, ये
oxygen.
oxygen.
Yes, very good. Now, now let's do the 53 question. What silicate structure is represented by the following illustration, guys? What will be the silicate structure?
Sir, phyllosilicate.
Exactly. And what is the other name of phyllosilicate, guys?
Sheet structure.
Yes, sheet structure. Exactly, sheet silicate structure. And 55?
Sir, iron single chain.
Yes, ionosilicate, single chain. Can you give me an example of single chain?
Pyroxene or pyroxenoid.
Uh, yes, but pyroxene is okay. Pyroxenoid is not a pyroxene, right? It's a pyroxenoid. Okay.
Yes, sir. Yes.
So please do not refer the term pyroxenoid. वो सिर्फ ओलास्टोनाइट को ही हम लोग pyroxenoid में और से बहुत सारे जो मिनरल है we actually consider that group of minerals in the pyroxenoid. So it's better to say pyroxene. Okay, please don't use the term
Yes.
pyroxenoid. Technically it's wrong. Pyroxenoid is wrong. So 57, I think it's very easy for you.
I know double chain.
Yes, double chain ionosilicate. And can you guys give an example of a double
Amphibole.
chain? Yes.
Amphibole.
Yes, amphibole. Okay. And okay. So yes, 62. Yeah, 62. Uh, anyone?
Sir,
Yes.
Sir, calcite.
is it
Calcite.
we?
Yes.
Nothing, sir. Nothing, sir.
Yeah, it's
Calcite,
calcite.
sir, calcite.
Yes. Now 64. Can you tell me which of the following mineral are built from the independent silicate structure?
Sir, is it option
Sir,
E, quartz?
No, not quartz. Quartz
sir,
is
sir, sir, A. Olivine.
why
Sir,
it will be olivine?
सर नेसोसिलिकेट जो होता है ना इंडिपेंडेंट सिलिका होता है
Okay, very good. It's an island silicate or an island type
स्टूडेंट
silicate.
सिलिका
Yes, nesosilicate. Yes, 65. Carry on. You guys are doing great.
From single chain.
Hi,
Pyroxene.
Nitin.
Double chain amphibole.
Yes, yes. Uh, okay. Uh, and which of the following mineral built from the seed silicate structure? 67.
Sir,
Please.
biotite.
Biotite, sir.
Okay. Okay.
Biotite.
Very good. Very good. Very good. And which of the following mineral built from the framework?
Sir, E. Sir,
Yes.
E quartz.
Quartz, quartz.
And why it is known as the framework, students?
सर 3D स्ट्रक्चर देता है.
Yes, exactly. It gives a 3D structure. So the answers are at this here. So you guys are all correct. We actually no need of seeing the answers because you guys have give all the answers you guys have provided to me are correct. So very good, students. So this is a very easy practice session, a basic practice session. Okay. So now, students, I think I will discuss the questions for the assignments, the 9 questions. Okay. Then we will end the class. So please stay with me more 15 minutes. Okay, students. We will just do the questions. I will just sharing the question, that 9 question. Yes. So can you see the screen?
Yes, sir.
So, please tell me, there are two minerals. As we can see that there are two minerals present on the display, right? There is a mineral A and mineral B. Now, the first question which has been asked here from the NPTEL course, that how many cleavages do you see in mineral A? So,
Zero, sir.
Zero.
Zero.
now, why it will be zero, student? How did you identify the mineral A? Because in order to tell the set of cleavage, first you have to look that if there is a possible set of cleavages or not. And if sometimes, for an example, let's say we know that calcite has 3 set of cleavage, right? The rhombohedral cleavage. Am I right or wrong?
Yes, sir.
So, but is it possible to see all the 3 set of cleavage in a calcite in a 2D plane? Is it possible?
No, sir.
It's not possible, right? So you can see the original hand specimen and then only you can examine all the 3 set of cleavage and then you can convey it to me that, sir, yes, there are 3 set of cleavages for a calcite. But by looking at the picture, you cannot be able to tell that it has how many sets of cleavage, right? It may be have some hidden set of cleavage which are not particularly visible in the section which we are seeing. It may be a possibility, right?
Yes, sir.
Okay. Now, so from this figure, how can you tell that it's a quartz? Because in order to identify the mineral, you need to have or you need to identify some kind of distinguishing property that to able to tell that what kind of mineral it is, right?
Yes, sir.
So what is the distinguishing physical property which is visible in this picture from which you can identify this mineral? Can anyone tell me? Anyone from this group? Anyone? Please go ahead.
Sir, conchoidal fracture भी.
Exactly. This is showing a conchoidal fracture. Now there is only one mineral which shows the most prominent conchoidal fracture, that is the mineral quartz. Okay. And how many cleavages do you see in this mineral B, guys?
One set.
Yes. And what is the name of the mineral?
It's a mica.
Muscovite.
Yes.
Muscovite.
Yes, it's a muscovite. Now, muscovite generally contains one set of cleavage. Okay. Now, what is the luster for this mineral A?
Glassy luster.
But I want to tell one thing, guys. See, in this question, what is the name of the luster of the mineral A? 4 options have provided: metallic, earthy, glassy, and pearly. But to be very accurate and precise, quartz has actually a luster,
Vitreous.
vitreous luster.
Yes, sir.
Yes, see, student, vitreous is not a glassy luster. Vitreous is a luster which actually resembles like a glass, but it is not glass. Okay, so it is preferred to remember that it shows a vitreous luster. For the exam purpose or any question purpose, it is glassy, right? But please always do remember it only shows a vitreous luster. And what is the name of the luster of the mineral B, guys?
Pearly.
Poorly.
Yeah.
Pearly.
Yes,
Sir.
pearly. And why not metallic, students?
सर मेटल अगर सर कोई मेटल होगा तो फिर वो मेटालिक क्लस्टर दिखाएगा लेकिन ये तो नॉन मेटल है.
It's partially correct. It's partially correct. What you are telling, I am satisfied. But देखो, I don't know, but there are some who consider that muscovite also shows metallic luster. ये क्यों होता है और कैसे होता है? I can just give you the basic concept, that is, anyone have you visited field? Anyone? Any field?
यस सर.
Yeah, so आपने do you have seen a muscovite in a field? I mean, आपने देखा है muscovite field में? Have you seen muscovite?
सर सर फील्ड पे नहीं देखा है लेकिन देखा है
Okay,
रियल में.
okay. So you have seen muscovite. So I am satisfied that it is pearly, and everyone knows it's pearly. Okay, but please do not confuse students that in some cases many teachers or many scientists usually say that sometimes muscovites show metallic luster. क्योंकि देखो क्या होता है, when muscovite is sometime when it is subjected to prolonged temperature, or let's say prolonged climate changes or temperature changes, उसका जो luster है, it's sometimes converted to some kind of a metallic uh, gloss. Okay, ये जो pearly nature है, it's been completely worn off, or actually it loses its pearly luster property. Sometimes it may be metallic, but it is very rare. Okay, if anyone tells you that if it is metallic luster, please don't go for it, because it is very rare. Because I have done a field in near Angul, Odisha. So in that time, actually I got a muscovite from the field, and it was not showing or not resembling like a pearl. So in that case, actually it has loosened its pearly property. Okay, in that frequent cases, we can say it's a different kind of luster, because due to weathering or erosion, or due to prolonged exposure of temperature or heat. Okay, but usually it shows pearly luster. Okay, so the mineral A has a three-dimensional network structure of silica tetrahedron. So what will be the mineral, guys?
Quartz.
Because it is showing a framework silicate framework structure, a three-dimensional arrangement, a triangle from the above and a same inverted triangle from the below. If you just flip the triangle and if you connect the triangle, you will get the tectosilicate framework. Am I right or wrong? Yeah, students.
Yes, sir.
Yes. So now the mineral A is often used in one household device. Can you guess what that is? What kind of mineral? Yes.
Clock, sir.
No. Okay. So you guys know the answer. It is clock. But why it is clock?
Piezoelectric.
Uh, Piezoelectric property. Yes. Okay. Let's say it's piezoelectric property. So what difference it will make if it does not have a piezoelectric property? Can you tell me? Please try it. Try
सर
it.
सर कैन यू रिपीट द क्वेश्चन.
So you guys are telling that mineral A is often used in household device. Okay. Now any one of the student has told me that quartz is used in clock. Mineral A is quartz and quartz are used in clock. So why these are used in clock? My simple question is that why you use quartz in clock?
सर जो अंधेरे में भी सर हम जो देख सकते हैं शायद से जो रेडियम बोलते हैं वो यूज होता है, लेकिन शायद से सर वो क्वार्ट्ज होता है।
हाँ क्यों, वाई वी यूज क्वार्ट्स, माय क्वेश्चन इज वाई। सो देखो, सी आई एम नॉट प्रेशराइजिंग यू गाइस, ओके, बट आई वांट यू टू नो द एक्चुअल आंसर, क्योंकि इन फ्यूचर इफ दिस काइंड ऑफ क्वेश्चन कम्स, आई आई होप सो दैट you guys will be able to clarify it, or you guys will be able to answer it very confidently. I want the confidence, because you guys will be facing different interviews after this point onward, right? So
यस सर।
you must know the actual concept. Why
Sir,
quartz?
vibration of quartz due to piezoelectric, sir, property.
Oh, okay, not due to piezoelectric property. Let me tell you what. So what piezoelectric is? Can you know, or should I explain it to you?
सर जो प्रेशर की वजह से सर जो होता है
Yes,
इलेक्ट्रिसिटी जो इंड्यूस होती है।
yes. So see, the actual is, देखो, क्वार्ट्ज में जो मॉलिक्यूलर अरेंजमेंट्स है, ओके, और द एटॉमिक अरेंजमेंट्स व्हिच आर प्रेजेंट इन क्वार्ट्ज, that are arranged in such a way, because the quartz is, first of all, it has a tectonic framework, right students? It has a three-dimensional network, okay.
Yes, sir. Yes, sir.
So due to that three-dimensional network, when the quartz mineral or quartz or any kind of quartz, okay, जब हम लोग जो normal quartz जो कहते हैं SiO2, when it is subjected to mechanical stress in terms of any kind of influence, it can be of tectonic influence, or it can be of any anthropogenic causes, or any kind of स्ट्रेस redistribution की भी वजह से हो सकता है, और ड्यू टू एनी फोर्सेस व्हेन इट इज अप्लाइड ओवर क्वार्ट्ज एंड इट इज सब्जेक्टेड टू एनी काइंड ऑफ मैकेनिकल स्ट्रेसेस, राइट? जब वो मैकेनिकल स्ट्रेस के अंदर इन्फ्लुएंस होता है, सो उसका जो एटॉमिक बिहेवियर है वो थोड़ा शिफ्ट हो जाता है। इट शिफ्ट इन सच अ वे दैट it can convey some arrangement that cause it to produce electricity. And we know what produces electricity: free electrons, right?
यस सर।
So due to the redistribution, or due to the arrangement of mechanical stress within quartz, so the electrons are set up, or the arrangement of the molecular pattern is in such a way that it can produce electricity. And the electricity is, when it is all over through that quartz, what it does, it start to vibrate, or it start to oscillate. Now this oscillation process has the ability to vibrate at a very precise frequency, okay. So क्या होता है? So what happens is, when the oscillation property is in action, it actually also um, tends to generate an ability, or to, that is, it makes the quartz to vibrate at precise frequency. And जब आपका कोई भी मटेरियल प्रिसाइज फ्रीक्वेंसी में वाइब्रेट करता है, इफ एनी मटेरियल vibrates in a precise frequency, it helps to regulate the movement of the watch, okay. जैसे कि आपका वॉच जब मूव होता है, आप देखिएगा, सो वी जनरली क्या करते हैं, व्हेन वी जनरली जस्ट फिक्स द वॉच, और समटाइम्स वी सी कि वो जो वॉच है वो उसका फ्रीक्वेंसी से, या फिर जनरली मतलब राइट टाइम से थोड़ा सा स्लो हो जाता है कभी कभी, ओके। ये आपका बैटरी का जो डिस्चार्ज है उसके वजह से भी हो सकता है, और अगर उसका अंदर जो क्वार्ट्ज का जो मटेरियल है, द मटेरियल ऑफ द क्वार्ट्ज व्हिच हैव बीन यूज्ड इन दिस बैटरी, it actually shifts from the preciseness of the vibrational frequency, okay। जब उसका vibrational frequency shift हो जाता है from its actual position, तब हम लोग का जो watch है वो हम लोगों का क्या होता है, हम लोग का dysfunction करता है। And to actually stop that dysfunctionness, we actually use higher quality of quartz, or very actual quartz, good quality quartz, so that the vibrational frequency, or the oscillation remains intact, okay. That is why we use quartz. Do you guys get it, the point?
यस
यस
सर।
सर।
yes so
सर
the,
क्वार्ट्ज हर वॉच में यूज होता है क्या सर?
yes quads we generally use quads in watch वो जो आपको बोला as I told you that due to its oscillator property so that it can able to maintain its vibrational frequency at very precise frequency that helps to regulate the movement of the watch, that's why we use quads. Okay,
यस सर, यस सर।
that's why you use quads. देखो there might be some alternatives okay other than quads, but to use that alternative the expense is very much. Okay,
यस सर।
for you guys you guys might have heard that there are many expensive watches, so in that watches guys use many things other than quartz, but those are very I mean, precious to semi precious minerals or metals we use, but that will make the price of that watch 10 folds. Economy is also a factor, right? So everyone cannot buy a watch of 10 lakhs or 20 lakhs. Okay, so yeah, it will be clock. Quartz is used in clock, and yes. So the mineral B is often used in iron. You used to get rid of the wrinkles of your clothes. Can you guess that mineral that is? Seven का आंसर क्या होगा?
मॉस्कोविच,
मॉस्कोवाइट।
मॉस्कोविच।
And
Moscovite.
and why it will be muscovite?
सर गुड कंडक्टर पे हीट होता है वो,
Yes,
मॉस्कोविट।
exactly. It's a very good conductor of heat, but bad conductor of electricity, right?
यस सर।
Yes. Okay. Uh, so can you tell me, out of curiosity, I am asking, जो have you guys seen diamond?
Yes, sir.
And you guys have
सर
seen graphite also, students.
Yes, sir.
So,
यस सर।
as we know, diamond is a what it is made of? It is made of carbon only. It's an allotrope, you may say.
यस सर।
And
Yes.
graphite on the other hand is also an allotrope. But student, graphite is a good conductor of electricity, but diamond is not. Why is that so? What is? I mean, please tell me the exact mechanism from which everyone can understand. Anyone?
सर अवेलेबल टू फ्री इलेक्ट्रॉन
In graphite.
इन ग्राफाइट।
Uh, yes, it is correct that available to free electron. But is there any change in configuration of the electron network inside
The
graphite?
bonds are very strong.
यस सर, यस सर, यस सर।
Yeah, can you specify what kind of pattern we see in graphite?
सर सर शायद ग्राफाइट में शायद जो कॉलमनार शायद ये जो हेक्सागोनल शायद होता है वो, पर वो पेंटागन होता है शायद।
Yes, you are correct, but जो आप जो hexagon when you are configuring that hexagon क्या होता है एक जो hexagon का end है ना वो आपका free रह जाता है okay, and that free end actually constitutes an electron.
यस सर, यस सर।
Yes, and that electron is readily available for pairing and moving. Because of that readily available free electron, it can conduct electricity. Okay, and
यस
one
सर।
and one more thing is this is also due to the close packing of the diamond. जो diamond we generally see diamond as an HCP structure. Okay, in the वो जो डायमंड हम लोग एकदम मतलब डीपर पार्ट से लाते हैं एट वेरी डीपर पार्ट, दोस डायमंड जनरली सी एंड मेनी टाइम्स इट्स एन एचसीपी ओके, बट क्या होता है व्हेन द डायमंड जो शैलो डायमंड्स जो होते हैं वो कभी कभी ऑल्टर हो जाते हैं क्योंकि हैव यू गाइस heard that sometimes diamonds show inclusions? Do you guys know about it? Or in the next class we will just discuss about there are inclusion in diamonds also. Okay, have you guys know or seen that there are inclusions in diamond guys?
नहीं सर। सर आप जो बोले इंक्लूजन सर वो शायद से आर्टिफिशियल तरीके से करने पर
Yes,
मिस्टर से नेचर में भी मिलता है इन डायमंड पे इंक्लूजन।
yes नेचर में भी इंक्लूजन मिलता है. See, when the diamond हम लोग एक्चुअली जो डायमंड है we actually find the diamond in kimberlite pipes. Okay, in Vajra Karur और Machagowan pipe. but so they are actually uplifting very fast with that Kimberlite hosts. But there are some diamonds due to some phenomenon, there are inclusions in the diamonds. They are actually pretty natural. We will discuss in the next class how actually that inclusion forms. Okay, but yes, and so the last question is,
Yes, sir.
what kind of silica tetrahedral structure does mineral B have?
Yes, sit.
Yes, exactly. So you guys have done the answers pure correctly. Very good. So I think that you will be able to do these kind of questions from further onwards, right, guys? Yeah, guys. Hello.
Yes, sir.
Okay, so what I see is your problem solving ability is quite great, and I think there shouldn't be any problem. So as a part of this TA, I actually have discussed the questions also. So I think जो questions हम लोग आज solve किए, the questions which we have solved today, that 30-40 questions, I think if that type of question comes, you guys will able to solve it because you guys know the basics already.
Yes, sir.
Okay. Okay, so today
Yes, sir.
here we will end the class. We will wrap up the class today, this session here. So students, I want to ask you one more thing. If you guys have any doubt or any question, you can ask me regarding the mineral part, that or the first week class. Okay. So I am here to clear all your doubts, or I will share my mail ID. So I am sharing my mail ID to you guys. So if any question you are having, you can directly mail me in this mail ID. Okay, wait a second, so that I will be able to clear all of your doubt. ठीक है, क्योंकि we will get only one class for a week, this 2 hour class, and everything is not possible to complete within this 2 hour because you guys might have some doubts, many extra doubts. So as a fact that I am also very busy, so but I can clarify your doubts, okay, when possible. See, I am sending uh, okay, do you guys got the message? I have just messaged right now. I have shared a mail ID, guys. Hello.
Yes, sir. Yes, sir.
Please note this mail ID for further contact. If any doubt is there regarding the course, you can forward that question in this mail ID also. I am here to clarify your doubts as much as possible, because there is an also extent to my knowledge also. Okay. So as much as I know, I will be just trying to convey it to you guys. So if any problem is there, please feel free to let me know. And you can forward your questions to this mail ID. Okay? And hope this will be good for you.
Yes, sir.
Okay. Okay. So today
सर
we, yeah,
Thank you, sir.
okay.
सर क्लास का पीपीटी मिल सकता है क्या सर?
Yes, so आपको PPT चाहिए. So do you guys have a common mail ID?
No, sir.
नो सर.
No.
Okay. So how will I share this PPT? Please tell me. मुझे आप बोलो, मैं शेयर कर दूंगा, मुझे कोई प्रॉब्लम नहीं. Is a single
Sir,
individual.
drive link.
Yeah.
Drive link.
ओके, सो क्या ड्राइव लिंक मैं आपको अभी दूं या फिर ओके ओके स्टूडेंट्स, ओके, आई विल डू वन थिंग. Is it okay if I give the PPT to you in the next class, because I have to upload that PPT in my drive and then only I can share you the drive link.
ठीक है, sir.
Okay, but
हेलो.
yeah, one